All right, thank you. It's great to be back in Cargèse. I'm going to show you quickly old and new results on properties and dynamics of large fault zones. These results have been obtained with very large group, including a decent subset that are actually present here, Michel, Florent, if I just look, Pierre, Orléans, Quentin, and a few other people. So I will spend most of the talk will be seismology, but I will also have maybe 5 minutes talking about dynamic rupture to address the dynamics part of the title that I was given. So fault zones have hierarchical damage structures that are quite complex with many elements, structural elements that you will see as we go along in the talk that are represented here schematically in these figures. Damage structure, significant damage structure tend to extend maybe 5 kilometers around large faults, but it has internal components with length scales of very intense damage with widths of maybe 100 meters and also very strong impedance of bimaterial interfaces that essentially have length scale or widths of 0 or from centimeter to 0. And so these are really complex structures that are difficult to both image and monitor. Now, all of these structures that you see here sits in a sub-grid in regional studies of the type that Anne Paul showed yesterday. So the question is, why should we bother? And the answer is, these fault zone structures are, of course, important for many things. One is they control the seismic radiation away from the fault, both locally but also on a regional scale. The reason regional scale may surprise you a little bit, but it's kind of obvious because the wave field that comes out of the fault zone is affected by the fault zone structure, and that wave field is now propagated to the far field. And very clearly, this has been demonstrated in numerical simulations, that when you include structure like this in numerical models, the wave field at all distances, regional distances, is completely altered. So this is one reason we want to understand the seismic wave field. You have to understand the structure to understand the seismic wave field. The other reason is, of course, we would like to derive earthquake source properties. And the accuracy of derivation of earthquake source properties depends strongly on your knowledge about the structure. This holds for locations, focal mechanism, sleep, and essentially everything else that you would derive. So this is another motivation. Third one is the structures are generated progressively by tectonic processes. And so in combination with mechanical models, understanding the structure helps understanding the physics that leads to the structure. Also, we will try to get to monitoring if I have time, but also this structure might produce some precursory changes, part of the evolution on a very short time scale. And to understand these precursory changes, again, we need to understand the structure. Static and dynamic stress fields can be understood, but just by looking at elements of the structure. I'll try to illustrate it a little bit. And this is both shear deformation and volumetric deformation. Similarly, by understanding the structure, we can understand the rheology that produces the structure, some particular elements of the fault zone structures, such as bimaterial interfaces and damage zones, can control future large earthquakes and reflect cumulative effects of many large rupture. I will actually illustrate this a little bit with my deviation on dynamic rupture. And if you need more motivations, fault zones also control crustal fluid flow. This was mentioned a bit in the previous talk. And so it's illustrated here very clearly. This is Southern California. Fault zones produce very high permeability along strike, but near zero permeability across the structures because of very, very dense gouge material that is compacted in the core of the fault zone. So fault zones are barrier to fluid flow across them, and you see this nicely in these lakes of actually oil production places in the Los Angeles basin. This is a figure from Egel-Hudson. And also you see this in the field in many places. So here is a fault. This is a bunch of the southern San Andreas fault. Later in the talk I will show you a subsurface image of this structure. You'll see how it looks below the surface. But the reason I put it here is because it's aligned with palm trees. These are natural palm trees, in contrast to the one you see in Los Angeles that have been planted. And they are here because the fault, which is right here, the fault trace, it's part of the San Andreas. Southern San Andreas is a barrier to fluid flow. So often we find oases, seg ponds, trees like this, they line across faults, okay? So I'm going now to try to illustrate all of this. Again, I'll start with imaging. I'll show a little bit about dynamic capture, and if we have time, I'll go to monitoring. So I will show many results from the San Jacinto fault zone in Southern California, where we deployed, over the years, we established hierarchical seismic network that is useful to image the hierarchical fault zone structure, because you need different techniques and different signals to image different elements of the structure. So here is the San Jacinto fault zone. It's the most seismically active fault zone in California in the last 50 years at least. And it is between the San Andreas fault, which is relatively quiet. This is the San Andreas fault to the east of it, and here's an Elsinore fault to the west of it. So we have a regional scale network. These are the blue triangles with length scales of hundreds of kilometers. We deployed linear arrays across different sections of the fault zone with various aperture and a number of instruments that vary from, say, 10 to 100. And then at one particular location right here in the center, SGB, with the help of Dan Hollis and others, we deployed in 2014 a network with 1,100 nodes. Very, very dense, very compact, 600 meter by 600 meters, sitting on top of the damaged structure of the San Jacinto fault zone. So we have very good sets of networks, and there are lots of signals that we are recording and analyzing in different frequency. And I'll just jump to results and show you. So I'm going to start with the lowest resolution results in the studies that I will show you. And I'm going back to an old study that was led by Amir Alam. This is a travel time tomography based on the regional network and the seismicity that you see here. So we have a modest amount of data, not huge, but sufficient, and it's a relatively low resolution. We have a grid cell here of 1 kilometer. And what you see, there are images here. These are P-wave velocities at different depth section, horizontal slices. 3 kilometers, 5 kilometers, and 7 kilometers. And these are vertical cross sections that cross this system of faults from the west to the east. For example, profile 6 is right here, very close to this very, very dense network that I showed you before. So what do we see? We see broad low-velocity fault zones that are illustrated on both sections. They vary along strike, but in all cases, there is a flower shape to those structures. They are maybe 3 to 5 kilometers at the surface, and they essentially become narrower, and they become faint below 5 kilometers in this resolution. So we have a prominent damage zones in the top 5 kilometer flower structure. They are offset, this is important, from the surface trace of the fault. Surface trace is 0, and we find everywhere that they are asymmetric, that on one side. There's a mechanical reason for this that I'll give you one possible interpretation for this. We have larger reduction of shear wave velocity. This is P, this is shear. So the shear wave velocity reduction are larger than the P wave velocity reduction. This leads to very high VP-VS ratios in the fault zone. So you get high ratios solely due to the existing of damaged structure. Cracked media is already having high ratio. On top of that, if you crack the media, you increase the permeability, you can get fluid. That's another reason. But we don't really need. It's important to separate. It's difficult, but important to separate what is produced by damage and what is produced damage and fluids. And we also have clear velocity contrast. You see it right here, for example, or you see here. If you look, you see here it's blue, it's fast, relatively fast, here it's relatively slow. But you also notice that the velocity contrast changes along strike. It doesn't exist forever. And this is a very typical feature of fault zones that we have reversed. The polarities flip because the rock bodies flip. And they flip on different scale. Everything here occurs on wide scale. So I'll show you later another example where we have a flipping velocity contrast on some smaller scale. But we don't know, these are velocity contrasts, but we don't know if we have sharp interfaces or it's just smeared because we don't have the resolution. It's a 1 kilometer resolution. So we will resolve it by looking at additional signals. And of course, we have other features that are low velocity. It's not only the damage zone. So there is a prominent sedimentary basin, for example, right here, associated. It's related to the Salton Trough, right here, that is bounded by the San Andreas Fault. So next, the other thing is not only we cannot resolve sharp interfaces, but we also don't have resolution for the top 2 kilometers of the crust with this technique, because the rays kind of come up vertically. So to get resolution for the top crust, we need to go to noise. So I'm showing you another old result led by Dimitri Zigon. This is noise imaging, 1 year of data, and we go up to 1 hertz. With this data up to 1 hertz, we have horizontal resolution similar to the previous study, 1 to 2 kilometers, but the depth now is more sensitive to the shallow crust, so we resolve well structure. I'll describe briefly some features. Between 500 meters to 7 kilometers. What do we see? Well, again, we see flower-type damage zones. So this is, again, a vertical profile 6, again. I like the number 6 right here. So here's the San Andreas Fault, San Jacinto Fault, Elsinore Fault. You see how it tapers. It's very prominent in top 3 kilometers. This is a illustration, a kind of effort to show in 3D the structure. So it's kind of interesting. Here's the San Andreas Fault. It's not active, as I said, but it has more prominent damage zone. This is the San Andreas, San Andreas, San Andreas, San Andreas. A good damage zone up to 5 kilometers, even in some places. And the San Jacinto is right here. The damage disappears at 3 kilometers. There are some places that the damage is deep. These places are near stepovers. So there are places in the structure that continues to conduce stress concentration all the time and seismicity, so there is damage there. But in parts of the fault that are relatively straight, it heals. We'll get to monitoring a little bit later and look at it. So this is what you see here. And we also performed joint inversion of Rayleigh wave dispersion based on this noise imaging and the body wave tomography I showed you before. This has been published by Fang et al. I'm not showing you results, but I will use it later. Later in the talk, I will show you results on merging velocity structure of different scales. And we're going to use the Fang et al. Model as a high-resolution model and compare the results with regional scale for the whole of Southern California, low-resolution model. So we'll use this result later. And then again, what's about the top 500 meters? We would like to actually get imaging all the way to the surface so we can compare with geological studies. That's what we want. So for this, you need to do higher frequencies. And here is another study led by Dimitri Zigon, where we use noise up to 35 hertz. Now we are using it, actually using just these arrays. And there are examples from all the arrays. You see how they are here in Google Maps on the surface. But essentially, we see a couple of interesting features here. Flower shape, again, with depths. So it disappears at even at shallow depths. All everything is hierarchical and keeps on occurring at different scale. Importantly, the velocities at the shallow crust reach 200-300 meters per second, which is very similar to what people measure directly with boreholes. And it's very important to understand seismic ground motion. It samples the so-called geotechnical layer that controls the motions that we record on there. So this is a very inexpensive technique to do that. And this figure shows that with about 30 days, you already get sufficient signal-to-noise ratio, in fact, even in 15 days, to do this kind of study. So it's a very efficient, inexpensive techniques. In some other studies that I'm not showing you now, we use the noise to extract Q values. So the Q values are very low, 5 to 30 in the top 30 meters of the crust. So it's highly attenuative material. And I make a comment now that will be connected to the monitoring. In the shallow part of the crust, we have very low velocities. The material is soft. It's highly attenuative. It's highly cracked. And the normal stress is connected to the fact that the normal stress is low. So because of this, the top material is highly susceptible to temporal changes of seismic velocities. Later in the talk, I will show you large changes. And they are dominated by the shallow structure. because of these properties and the low normal stress. Okay, so I showed you what I showed you. We would like to now look deeper inside in inner smaller components. And so I'll show you some results now on fault zone head and trapped waves. That takes me back to my PhD thesis, which is the time more or less where I first met Michel, and he came to visit Keyaki, shown here in this picture. Let's start with head waves. So if you have two materials now, this is very simple, and amazingly it actually works. It fits data very well, as I will demonstrate. So suppose you have just two blocks that are in contrast, and you have earthquake close to the interface, bimaterial interface. If you have station on the slow side of the fault, closer to the fault than this critical distance that depends on the propagation along the fault and on the velocity contrast, the first arriving seismic phase is not the direct P wave, but a head wave that spends most of its propagation along the interface, propagating with the velocities of the fast side, and then from the interface leaks to the slower material. So this is a smoking gun. This is a refracted wave, and it tells us it's a smoking gun for a sharp interface that is continuous between the source and the receiver. We'll use it later. Now, if I add a low velocity layer, and this is here is a picture with Keyaki a couple of years before he passed away. If you add a low velocity layer, you get, in addition to the head waves, which are shown here, these are the head waves. They are emergent, weak emergent phases. On top of that, we get trapped waves, essentially guided waves that are resonance mode inside the structure. We can use this for imaging. Now, bimaterial interfaces can affect significantly earthquake rupture properties, as I will demonstrate, with some results from dynamic rupture studies and with some observations as well. The damage zones reflect the cumulative effect of many ruptures. So they show us what the fault zone tends to do statistically over the long term. So they are important components. Let's have a little excursion, 5 minutes maybe, looking at dynamic rupture in structures with bimaterial interfaces. So an example of a nice bimaterial interface that you see at the surface. So I'll show you quickly very blend of analytical and numerical results. So Wirtmann in 1980 solved 2D analytical solution for steady state mode 2 slip holes on a frictional bimaterial interface in a configuration that is shown here. So there are two materials compliant on the top. This would be low velocity, stiff, high velocities at the bottom in this configuration. And there are some loadings, remote loadings, normal stress and shear stress. And the displacement field is U. The difference of U above the interface and below the interface is the slip, in-plane slip. Now, this is a steady state problem, so we use a moving coordinate system denoted by this letter xi. And one important quantity that controls the fields is the special derivative of the slip, which is called dislocation density. So what Wirtmann showed, this is a solution of Wirtmann, that the dynamic shear stress during the propagation of rupture, shown here, is given by the remote loading, whatever you put there, that's the background, plus some mu bar algebraic function of the shear wave velocities and the contrast of velocities, rupture velocity, C, and contrast of velocity across the fault, multiplying the Hilbert transforms of the dislocation density. So this kind of solution appears also without velocity contrast, and I'm showing you here mu bar for different kinds of contrast, including 0. So when when the shear wave velocity contrast is 1 across the fault, there is no contrast. When the shear waves ratio, is 1, there's no contrast. This is mu bar, and those lines with dash dots all the way to dots, increasing contrast up to 20%. Okay, so this is a standard solution actually. The surprising result in this problem comes from the solution for the dynamic normal stress. The dynamic normal stress, in contrast to a transform of the shear dislocation everywhere along the fault, is locally controlled just locally by the local dislocation density, which is very high, right behind the rupture tip, and then becomes weak. So right near the rupture front, this is high, B, and there is another algebraic function, mu star, which is shown here. So mu star is 0, identically if there is no contrast, if the ratio is 1. But if there is a contrast, mu star increases rapidly as the rupture speed increases toward the Rayleigh wave speed. So So mu star can be really large for high rupture speeds near the Rayleigh wave velocity, which occurs very rapidly. When rupture propagates, it right away jumps to the near Rayleigh wave velocity. And it's very high when the dislocation density is high, which is behind the rupture tip. So now, this result that I'm showing you is this sign convention that mu star is positive is hold for the tip of the ruptures that propagates in the direction of motion of the compliant block. The motion of the blocks depends on the boundary conditions. The direction of rupture, the rupture can propagate in both directions. So in the direction, the tip propagates in the direction of the compliant block, mu star is positive, and we get dynamic reduction of normal stress, which can be very large near the rupture tip. On the other hand, in the opposite direction, right here, the results are similar, but it's a negative sign, it flips. So the normal stress increases dynamically. We have opposite signals. So what happened, and there's one piece of analytical solution, this effect that I'm showing you increase with propagation distance. So the consequence of this reduction of normal stress in one direction, increase of normal stress in the other direction, produces a transition, a spontaneous transition from bilateral rupture. So you see here numerical simulation. Apologies for this very old plot. But this rupture here starts bilaterally on a bimaterial interface, which is in the center here. In this direction, the normal stress decreases. So the rupture propagates happily with less and less resistance. In the opposite sides, the normal stress increases. So it stops the rupture, and we get from initial bilateral, it evolves eventually to unilateral, right? So here are blow-ups of these plots. This is a rupture pulse. So the only thing that is slipping here is this little box right here. And the colors are particle velocities associated with the waves now radiated from the rupture. So you see here the P wave front on the slow side, P wave front on the fast side. Here is a head wave right here. And we look at the blow up. This is a blow up right around this little pulse. You see the particle velocities across the interface that produce dynamic dilation here, dynamic compression here. And the results of all of this is that we expect preferred propagation of subsonic ruptures in the direction of slip on the compliant side of the fault. And we also expect rock damage asymmetry across the fault, because damage is generated, I can show you a simulation on this too, but it will take too much time. Damage is generated preferentially on the tensional quadrant of the radiation, which would be here. So if rupture tends to propagate in this direction, we're going to get damage preferentially on one side, and we would expect to see asymmetric rock damage across the fault. I'll show you later results, if you want, that demonstrate this. Okay, so let's now look at back to the San Jacinto fault zone. Here is a figure that I already showed you. So we have velocity contrast, but with flipped polarity. And this is a result trying to resolve different things, including rupture directivity, by looking at particle motion in different azimuths generated by many earthquakes. And so you see the result here. On this part, where we have contrast like that, the top is faster, we get preferred propagation direction of earthquake rupture, shown by these blue arrows, to the northwest. This would be consistent exactly with the theoretical prediction, based on the fact that this is a right lateral shear. So you see the motion of this block is to the left, that's where the earth will go. When we switch to this part of the fault, with the velocity contrast flip, the direction of the preferred propagation direction flips also. So this is a very interesting, very small earthquakes. So, there are different ways of inferring. In this case, it just is done in the time domain. I have another set of studies that we use second seismic moment, more fancy technique, and we get consistent result, but with a smaller data set, because then you need better data. So we have done it with several techniques, and we get consistently results like this. So this is consistent with the prediction. Don't know what happened, but okay, we recovered. And I also want to show you that there are normal orthogonal ruptures as well, which is kind of was surprising at the beginning, but it's not surprising anymore. Now I'm very comfortable with it. After 10 years, we see normal structure, orthogonal structures everywhere. Incidentally, orthogonal structures are not consistent with frictional studies. With frictional physics, you would expect conjugate sets that are up to 60 degrees. We see orthogonal structure in many places. That's another topic we can talk about a little bit later. But this is a beautiful illustration of orthogonal structure in aftershocks of the 2016 5.2 Borrego Springs, which, by the way, was recorded on some of our arrays. And you see it's also on the surface traces of the map. Okay, so we have that. Now, I want to show you another case where we have interesting results. It's a famous place, Parkfield. So Parkfield, there were a sequence of earthquakes that propagated to the south. What is it here? It's southeast, actually. Couple of earthquakes. But then in 2004, there was an earthquake that started here and propagated to the other direction. So let's look at the velocity structure. And here is the velocity structure. This is a very old tomography from 1993 by Everard Phillips and Andy Michael. When you look near the hypocenter of the magnitude 6 earthquake, the top material is clearly lower velocity. But when we move to this place, this contrast disappears. In fact, Cliff Thurber did a more detailed tomography in 2016. This is a quote from his paper. So he basically claims that, that there is a high velocity body, that the contrast flips, not only disappears, but flips. So the results at Parkfield that I showed you so far, I mean, these earthquakes are very limited data set, but they're in fact consistent. We see reversal of the polarity, reversal of rupture propagation direction. There are some studies now also with small earthquakes, more larger data sets, consistent with what I'm saying. In this area, the consistently directivity tends to be to the left and here to the right. Back to the seismic imaging, San Jacinto Fault. So I'm now going to show you sets of results from different arrays. We're going to march quickly. I'm going to start from the south. Here, this is a JF, Jackass Flat location. Here is the array. The colored symbol indicate earthquakes that produce trapped waves across these arrays. Here is an example of waveform observation and waveform modeling. So we model it using this super simple solution. And as you can see, it explains most of the data, not all of it, but most of the data. So these are very good waveform fits. Here are the trapped waves. The trapped waves, even in this simple solution, depend on 6 parameters. So it's important not to do, how did you call it? What you advertised on inference mode, but to do actual inversion to study, I know, but you use, it's important to study the parameter space study to understand the trades-off. So we do this. We have genetic inversion algorithm that is sampling the parameter space. There are clear peaks, probability density peaks, that are giving you these parameters here. These parameters change as we go along strike, but they stay in the ballpark, same. So the inner damage zone that produces trapped waves is about 200 meters, 100 meters to 200 meters. The depth is up to 3.5 kilometers, roughly. Shear wave velocity reduction of 50%, Q value 20. And again, it's interesting that it's asymmetric. Everything I show you is asymmetric. Here is the regional tomography from the paper with Amir Alam. So this is the fast side of the fault, this part. It's the fast block. Now the main structure of the San Jacinto fault is right here, the Clark fault. And all of this damage structure is offset onto the faster side. That's exactly what you expect theoretically. Okay. Now I go to the dense array. So here is the dense array, and here is the regional velocity contrast. This is fast here, slow on that side. We have done many studies here. I only can give you a sample of this. So I picked this study by Mordret et al., and I'm only showing you one image. Here is a tomography at 200 meters, wrapped on the dense array locations. So this is a local basin structure. Here there is a trapping structure. We detected trapped waves here, and it is on the side that is the faster side on a large scale at seismogenic depths. Okay, we have more studies here. I don't have time to show you. This is a very cool result that was already discussed several times by Alex showed it and explained it. Michelle referred to it. This is back projection of scattered wave field. So we go away from the continuum waveform results that I showed you so far, looking at actually cracking. And you see nicely zones with high crack density, which reflect the damage structure. And there are multiple features that including dipping structure, which are interesting. I'm jumping quickly further to the north. So here is another array Here it's a sort of similar. So we have trapped waves. They are offset. They are on one side of the fault. You actually see this is the damage structure right here. We can model this, but I'm not showing you. Instead, I want to show you head waves, which I didn't so far. So we also detect head waves. Here is the head wave. This is the P wave. If you plot the move out between the head and P wave, you can get the average velocity contrast across the fault using this simple solution. We infer 10% velocity contrast going back 50 kilometers from this site. And remember, if I go further to the south, we also have velocity contrast, flip polarity. I don't have time to show you. This is a new result that I already showed you this figure. So this is another experiment on the San Andreas fault this time. Here is the San Jacinto fault right here. So far we talked about this. If I go to the east, this is the main, the spine of the plate boundary is right here. It's not very active now, the San Andreas. There are two branches actually here. Faults, when you look closely, are complicated. Even the San Andreas has two branches. One is called Benning fault, and to the left of it is the famous Coachella Valley. But the other one, this one, is called Mission Creek fault. Right? So there are two of them. We have a nodal array with maybe 300 stations. It's a combination of linear and two mini 2D arrays. And my postdoc, Guolian Lee, has been now working on double difference waveform tomography, just using this dense array. And you see results for the Benning fault, both Benning and Mission Creek fault. Interestingly, there is low velocity and high VP/VS for both faults. But the VP anomaly is shown only on the Mission Creek fault. So there is a very, very high VP/VS ratios. And it's dipping, as you could see, but only in the top 3 kilometers. And we lose resolution, but it looks like it's changing to vertical. All of these things are very important if you try to understand the wave propagation from this fault. Okay, so now I showed you a bunch of results on different scales. And there are more I haven't shown you. And now we have a regional model, also regional velocity model. So a very important question is, how do we combine all of these studies so my local velocity model don't just float in vacuum, but are residing in a well-organized library, if you want, of coherent knowledge. So how do we combine this? There are different techniques. Standard technique is just to embed. You take something like this, and you stick it, or like this, stick it in the larger scale model. This is not good, because you create artificial boundaries that even with smoothing remain. But the other part is there are big holes around them. So the information content changes as you move in the model. So a better technique is to do something that is associated with style transferring, that we use the high resolution information to populate information in the regional model. And that's what I'm going to show you. This was published earlier this year. So suppose you have overlapping regions with different resolution. Here is a regional model, and inside I have a inner region with high resolution study, and they overlap. So what we do, we compare the results in the overlapping region. We develop a transformation in the overlapping region between the high resolution and low resolution. And then I use this transformation to populate the entire regional study, regional model, and increasing the resolution like this, artificially, if you want, with style, but we're going to test it and see that it works everywhere in the region. So here is the method. We are using dictionary learning. Here is an overlapping region, which is part of Southern California. So I have only this part overlapping region. Imagine you have a pixel somewhere here. So you have a pixel, so we represent the image in terms of basis functions, images basis function. We use only 20. So here is a low resolution dictionary, and here is a high resolution dictionary for the same region. This uses the Fang et al. Model that we derived for the San Jacinto region. And now we develop representation that each image, each pixel here is represented as a linear combination of these basis functions. And the trick is, the key here, is that we use the same coefficients for the low resolution and high resolution dictionaries. So the dictionary differ in resolution, but the coefficients are the same. And then what we do, it works almost like magic. We go to the regional model. We develop this. We produce this sparse representation everywhere. but we flip the dictionaries. We use the high-resolution dictionary everywhere in the model. So let me show you how it works. Here is the results from Zigon et al. This is VS at 2 kilometers. This is VS of the SCEC community model that took, say, 20-some years to develop. It's a lot of investment. It's good. It's regional, large scale. It's relatively low resolution. I'm showing you results 9 by 9 kilometers. This is 1.5 by 1.5. Here is the reconstructed model. So we are using features from both the low resolution and high resolution, the regional. We preserve everything, but it's much smoother. This is a similar illustration for VS. Here is results from Fang et al. This is the SCEC community model, and here's the enhanced model. Smoother. It looks good, but of course, looking is deceiving. We're going to need to test it quantitatively. It's most impressive on VPVS ratios. This is the VPVS ratios of the SCEC community model. Pretty patchy. Clearly, lots of artifacts here. This is VPVS ratio from the Fang et al. Model. This is the enhanced model over the whole, the enhanced, reconstructed model on a regional scale. Looks much better. But as I said, looking is nice. Can we actually validate? Yes. So what I'm showing you here are waveform simulation from 5 earthquakes, spread here, shown by the beach ball, recorded at 22 stations, shown here. And you see the observations in black, the simulations using the original SCEC community model in blue, and the simulation using the enhanced model in red. And almost everywhere, the enhanced model performs better. These are the cross-correlation coefficients between the simulated and observed waveforms. And if I I just add the cross-correlation coefficients everywhere at all the stations, 22 stations, we have gain in the cross-correlation coefficient factor of 2.75 on the average with the enhanced model. So it does work. On the average, it produces better fits to earthquake waveforms than the original model. So I'm now switching to temporal changes of seismic velocities. How much time I have? It will dictate the details that I get into. 10 is good. For everything, I'll be very fast. So I'm going to show you, I'm going fast, but the idea is to illustrate some features rather than to get to technical data. So I will highlight a few features that are recurrent in many of the studies. This is a famous kind of classical result from Laurent that serves as a good starting point here. So this is a cross-correlation based inference on temporal changes of seismic velocity. Here is Parkfield earthquake. So there is a little delay. This is San Simeon earthquake. The important point is, what's the important point? The cross-seismic changes, there are two features I want to highlight. The cross-seismic changes resolved here is 0.06, 10 to the minus 2%. Very, very small. Now I will make an argument. I will prove that if I use smaller and smaller time steps, so this is used about 30 days time step to stabilize the result. But if I now have another technique that uses smaller and smaller time step, we're going to go from 0.06 to tens of percent very quickly. We get very large changes. This is my first point. The other one is there are some features that are ubiquitous, seasonal and daily variations. So I want to study them as well, because they are actually with large amplitude if I use small time step. So that's what I'm going to do with multiple techniques now. So time steps of second reveals much larger changes in the shallow crust. You'll see why I'm saying this. So here's an illustration. This is from Japan. This is from a paper led by Fabian Bonilla. After the Tohoku earthquakes, this is a station somewhere, a high-net station, picked randomly almost. It's seen on many stations. So here are the Tohoku earthquake seismogram recorded at the surface. And this technique uses autocorrelations, not cross-correlations. Autocorrelations, so we have 5.2 second moving time windows, 80% overlap. The temporal resolution is 1 second in this technique. And we observed 50% drop. You see it right here. We get some changes of time, and then we convert it to velocity. 50%, 5.0. And this is not, it could be even larger than that. I can explain to you physically what's going on later if we get. So we infer that this is in the top 100 meters. In some other places, we use borehole data, so I know that there are changes like this in the top 20 meters, actually. And if you go below 20 or 30 meters, the changes drop, almost no changes. It depends on the location. But anyway, that's the result here. So we get 50% drop in the subsurface. And Nakata and Snyder used many other boreholes. So they showed 5 to 10% with larger time steps. The one I'm showing you here, 1 second is really a sophisticated technique in the top 100, 300 meters over much of Japan. Okay. So temporal changes of shallow materials are widespread. They are very large. That's a big challenge that I'll try to, in my last slide, I'll get to this. How do we look at what's happening deeper? Because these large changes mask what's happening at depths. Here is another same technique with Fabian Bonilla. We use the dense array. Here is a accelerogram acceleration generated at this station right here by small earthquake, 2.3, 10 kilometers away from the array. We can convert it to velocity. Here's the envelope of velocity stack across a whole column here. So here is this. Once I have velocities, we can use changes in velocities and get temporal changes. So here are changes of velocities everywhere from this earthquake. Red means, so before the earthquake, it fluctuates, red and blue. Then there is an earthquake. It's still noisy, fluctuates, but there is a reduction of velocity. And after some time, relatively short time, it recovers again to fluctuations. If I stack everything, this is what we get. We get 20% change. It's a big number from 2.3 earthquake that occurred only 10 kilometers away, right? And we see this with other earthquakes. Here's a study with Yang Lu following a big earthquake. So this is the Ridgecrest earthquake, magnitude 7.1. But the interesting thing here, it also uses autocorrelation, and we are using 8 minutes time window. But the interesting thing is that we see widespread changes over 100 kilometers away after these earthquakes, which heal very fast. So you see locally, very close, there's a big drop followed by logarithmic healing in this case. And this shows you how it changes with time. So with the exception of very close to the rupture zone, it heals very quickly. It's very, very shallow and heals very, very quickly, after a week or two. So here's the results from borehole in the Garner Valley, which is adjacent to the San Jacinto Fault right here. Vertical array of seismograms with boreholes. We use autocorrelations after the El Mayor earthquake that occurred some 150 kilometers to the south, far away. We see big changes, 20%, essentially, but at 6 meters. I can look at different sensors now, 6 meters. And if I go to 20 meters, I still see changes, but below 20 meters, the changes are negligible, very, very small. So there are big changes in the shallow crust. This is one of my last slides. Maybe I have one more, I think, after this. So this is a regional study all over Southern California. We use all of those stations, 50 stations. And we looked at daily and seasonal changes. Here is daily, here is seasonal, and the amount of change these are noisy figures, lots of colors, but it's reflected by the color attached to the station. So here's an example of how we do this. This is, in fact, the surface station at the Garner Valley that I already showed you results before. So we validate this technique. Now, so we are using, this is a new technique, interesting technique. We are combining age-over-V ratios with autocorrelations. And we get something that we call deconvolved autocorrelation. You can look at the paper, but the important message here is that we see widespread changes, daily changes, up to 10%, actually. No, daily changes, where is it? Yeah, the daily up to 10%, very surprising, very, very shallow, from 0 to 10%, depending on where you are, but they are everywhere, there are changes. This shallow crust is moving all the time. Seasonal also, all the time, moving and changing. It's in the top 20 to 100 meters based on the age-over-V ratios. We estimate the surface layer width. So this is produced by combination of fluid and temperature effects. And I want to highlight the effect of temperature because it doesn't get enough attention. The temperature at the surface is very important because it affects, first of all, the soil moisture that other people are arguing that is very important, but the soil moisture depends on the temperature. The temperature affects the soil moisture. It also affects the barometric pressure above the ground that also produces changes. And on top of that, it produces thermoelastic strain, which also changes the fluid content. So temperature is underappreciated. It's actually the engine of many other things. It's the engine of the weather system. It's temperature changes on the surface of the Earth. So that's the last one before my final. Okay, so this is one more study in Oklahoma now with another group using cross correlations. Here is a network of stations. These are the estimated temporal changes of velocities. The long-term changes correlates quite well with estimated of water level based on GRACE data. But you see all of these decorations, seasonal. So this group concluded that this seasonal variation are produced by thermoelastic strain. You see the surface temperature, the red, noisy red. This is model thermoelastic strain, the dashed line, and it fits the data reasonably well. Again, the temperature, as I said, also affects the soil moisture and other things. So it's really important to consider. Okay, so my last slide. Everything I showed you on the temporal changes is very shallow. And the question is, how do we look deeper? It's an unsolved problem. But Laurent started a project a couple of years ago called fault scan. And he already talked a little bit about it. And the idea is that you use repeating sources. In this case, we use repeating anthropogenic sources. Trains running in the Coachella Valley that is bounding the San Andreas Fault. These trains produce repeating signals. You can analyze, you can detect the signal, analyze them, and look at temporal changes. We started this, several years ago in 2019. So maybe, and the fact is that so far we did not find clear temporal changes. We are monitoring the San Jacinto Fault. There was maybe a small change, maybe associated with slow slip, but we did not find temporal change. I showed you that if I look all over Southern California, we see big changes all the time, but they are shallow. Deep is another story. So we are not giving up. This still continue, but I just want to make the point. We haven't found yet with this technique, which is very accurate, and it bypasses the shallow crust by using body waves that propagate depth. So this work still continues with Yishao leading some works, Quentin leading some other works, and this is it. I stop here.